Today, we are diving into a really fascinating and, let's be honest, a pretty wild paper that asks us to totally rethink something we see all the time: moonlight. The author puts forward this really bold theory that, well, it challenges a lot of what we just take for granted about light and heat. Okay, let's get into it.
So this is the big question that kicks the whole thing off. I mean, we all know sunlight feels warm, right? But what if its reflection, moonlight, does the exact opposite? What if it actually actively cools down the things it shines on? It's a totally counterintuitive idea, and that is precisely what the author of this paper sets out to explain. And get this whole idea didn't start in some fancy university lab. Nope, it bubbled up from the internet. You had these amateur experimenters posting videos online, and they were claiming to show that objects under direct moonlight were measuring colder than objects in the shade. Seeing all this, the author we're looking at today decided to dig in, not so much into the videos themselves, but into the actual physics that could be behind such a claim. Okay, so before presenting his own theory, the author first takes a really close look at the people trying to debunk this whole cold moonlight idea. He basically starts by arguing that the mainstream rebuttals aren't just unconvincing, but that they are, in his view, just fundamentally unscientific. Here's a quote from a prominent debunker, Mick West, and the author uses this as a classic example of what he's talking about. It's dismissing the idea through authority rather than actual evidence. The argument is basically, hey, if this were true, we'd for sure already know about it. The author just breaks this argument down piece by piece. First, he says, look, that assumes science already has everything figured out, which it doesn't. Second, it just assumes the conclusion that it's false, without even testing it. He also points out that a lot of debunkers just pivot to talking about the moon's brightness, which nobody's arguing about, instead of tackling the question of the quality of its light. For the author, this all adds up to one thing: the core claim is never actually being tested. And the critique doesn't stop with just the logical arguments. It moves on to an actual physical experiment. The debunker, Mick West, used an infrared camera to check the temperature of a wooden table that was partially shaded by a plank. But the author of our paper argues this test was completely flawed, basically claiming it was set up in a way that would make finding any kind of cooling effect next to impossible. So the author points out several specific issues here. First, the picture was snapped immediately, with basically no time for any real temperature change to happen. Second, the table was already showing up as dark blue, which is the coldest color on that camera's scale. So, how could you possibly see if it got any colder? And finally, the original claims from the internet were about water cooling down, which was never even tested in this experiment. All right, so after making the case that the debunkers haven't actually disproven anything, the paper pivots. It starts to offer its own explanation for what might be going on. And this is where we get to the core of the theory, and it involves a new proposed particle the author calls an antiphoton. So, what in the world is an antiphoton, according to this theory? Well, it's not some exotic antimatter. No, the author proposes it's just a regular photon, but it's spinning in the opposite direction from the photons around it. And the key idea here is that this little spin flip happens whenever light reflects and just changes direction. So the proposed process is actually pretty straightforward. First, you've got sunlight traveling from the sun all the way to the moon. Then it reflects, it bounces off the surface. That bounce reverses its direction of travel, so it comes back toward us here on Earth. And according to this paper, that simple act of reflection is all it takes to turn these photons into antiphotons, at least relative to the light that didn't bounce. Now, to make this feel a bit more intuitive, the author uses a really simple analogy. Imagine holding a clock. Its hands are moving clockwise, right? But if you turn that clock around so it's facing away from you, from your perspective, the hands are now moving counterclockwise. Nothing about the clock itself changed, just its orientation relative to you. The paper argues the exact same principle applies to the spin of a photon. And this is how we get to the cooling effect. So when these antiphotons with their opposite spin arrive from the moon, they hit objects on Earth that have already been energized by regular photons from the sun. The theory goes that these opposite spins then partially cancel each other out, kind of tamping down the total energy of the object. And what is less energy? Well, it's less heat. So the author then tries to connect his whole theory to a known, totally accepted scientific phenomenon: laser cooling. He argues that science has actually already observed this effect, but he claims that they're explaining it with a totally flawed model. Yeah, check this out. You can see the two explanations right here. Mainstream science explains laser cooling by saying atoms absorb photons and lose momentum. But our paper finds this pretty illogical. It asks, how can absorbing energy lead to cooling? Instead, it proposes that by firing lasers from opposite directions, scientists are accidentally creating antiphotons, and it's the cancellation of those opposing spins that's really causing the temperature to drop.
But the theory doesn't stop with just cooling. The author also uses it to try and explain another weird property of moonlight, the way it kind of messes with our perception of color.
Have you ever noticed this, that on a really bright moonlit night, the whole world seems to have this distinct bluish tint to it? Well, that's a real thing. It's called the Purkinje shift. But why does it happen? So the standard explanation is all about biology. It says that in low light, our eyes switch from using our color-sensing cones to our more light-sensitive rods. These rods aren't great with color, but they happen to be most sensitive to blue-green light, and that's why the world looks blue. But this paper offers a physics explanation instead. It says the antiphotons in moonlight are better at canceling out the lower energy colors, like red and yellow, leaving the higher energy blue light as what's left over for us to see. And this brings us to a really crucial point in the author's whole method. He claims that just pointing a fancy instrument at the moon and seeing a full spectrum of light is a total misdirection. The really interesting stuff, both the cooling and the color shift, that only happens after the moonlight actually interacts with objects here on Earth, where that whole spin cancellation thing can take place. The author wraps it all up by basically positioning his work as totally independent of any established camp. He accepts the fringe idea about lunar cooling, but then provides this brand new physical explanation for it. He's rejecting both the mainstream dismissal and some of the other wilder conclusions people have drawn. He's trying to carve out what he calls a third path. So look, whether you find this whole theory plausible or not, it forces you to consider a really fascinating question. The paper's biggest challenge isn't just to the established facts, it's to the methods and the assumptions we use to discover them in the first place. It kind of asks us to think about what we might be missing when we assume we already know exactly what to look for and exactly how to look for it.